We want to welcome everybody for joining today's webinar, How to Calibrate Pressure Instruments Part 2. This is co-hosted by ISA and BMAX. My name is Michaela Cooper. I'm with ISA and I'll be hosting today's webinar. And before we get started, I would like to review a few housekeeping items and let you know how you can participate in today's session. First, in regards to the question and answer sessions, or the Q&A sessions, we have two Q&A sessions today, one 10-minute Q&A within the presentation, and another session at the end. If we are unable to get to your question during the first Q&A, we will hold it till the final Q&A session. And to submit your questions, simply type them into the Q&A box on the right-hand side of your screen. If you're viewing along with others at your site, please designate a scribe to submit your group's questions. Do not use the chat toolbox for your questions for the Q&A sessions. I repeat, do not use the chat toolbox, use the Q&A box. If you have miscellaneous questions for me, the host, submit those into the chat toolbox. And unfortunately, with this large amount of pre-registrants, we cannot open the phone lines for questions. If we do not get a chance to respond to your question, or if you would like to discuss a topic more in detail with one of the presenters, feel free to contact them directly. And that information will be given at the end of the webinar.
I saw on there where it talks a little bit about the drums, the drum levels.
Everybody needs to make sure that they are on mute. We are keeping the phone lines closed for this webinar. Second, for those of you who just joined, like I just said, make sure you are on mute. If you would like to see the phone and audio broadcast connection instructions again, please refer to the confirmation email I sent to you today, or if you go to the top left-hand side of your WebEx screen, you will see a tab labeled Event Info or Meeting Info, and some of those connection instructions are included there as well. Also, once this webinar closes, a survey should pop up in your browser. You'll want to take just a few minutes to fill out this survey and tell us about your experience at today's webinar. In particular, there will be a question about what topic you'd like to see us present for the next webinar, and please provide us your feedback. We want you, our audience, to help us determine what the next webinar should be on. Additionally, this webinar has a video component. If you'd like to make the presenter's video larger, you can just double-click on the video and it will enlarge on your screen. You'll note that once you enlarge the video, you will no longer see the slides. So if you want to click out of the enlarged video screen, click on the button in the right-hand corner that says Exit Full Screen View, and you will be able to go back to the main view like you're seeing right now. You can also enlarge the presenter's video screen and also see the presentation slide along with it by sliding that right-hand panel over back and forth. If the video component isn't loading well for you, you may need to connect somewhere with better internet bandwidth or connect your computer to a direct internet line. If you are listening through your computer and you have poor internet connection, the audio may not align well with the video. In this case, I would suggest that you dial in through the phone for a much more clear audio. Once again, those dial-in instructions are on the Event Info tab or on the confirmation email I sent to you today. Next, I'd like to tell you a little bit about our presenters. Roy is a professional services engineer with BMAX. He has been teaching calibration management for 14 years. He has taught on 4 different continents to people from over 40 countries. Roy has worked for Hewlett-Packard as a corporate trainer managing worldwide training activities. He was also previously a key player with Honeywell at their Fort Collins, Colorado office, where he supported the document calibration management software and Honeywell's 2020 portable calibrator as a trainer, certified developer, and technical advisor. Roy holds a BS in Computer Information Systems from Regis University, and an AAS in Electronics Technology from Denver Institute of Technology in Denver, Colorado. Today, Roy conducts educational training sessions and provides technical support to BMEX customers. Next, we have Technical Director Ned Espy. He has been promoting calibration management with BMEX for 20 years. Ned has helped develop best practices for calibration with a focus on pressure, temperature, and multivariable instruments. He is a consistent editorial contributor to leading industry publications and has received significant recognition within the automation industry. And recently, Ned contributed to the 416-page book, The Engineer's Guide to Industrial Temperature Measurement. Last year, he wrote a paper titled Improved Measurement and Control Utilizing Advanced Calibration Strategies, which he presented at the ISA Power Industry Division Symposium, June, and at the ISA Food and Pharmaceutical Industries Division Symposium, February. He will be presenting a new paper titled Meeting AMS 2750 Accuracy Requirements for Calibration at the ISA International Instrumentation Symposium to be held in Huntsville, Alabama, May 12th through the 14th. And today, Ned consults on calibration best practices and provides technical support to end users as well as the BMEX sales team in North America. And last but not least, we have Hunter Vegas, who has worked in the automation industry for nearly 29 years and has executed over 2,000 automation projects in the nuclear, pulp and paper, and specialty chemistry industries. He is a frequent contributor to several controls magazines and recently co-published his first book, 101 Tips for a Successful Automation Career, along with Greg McMillan. Hunter currently works for Wunderlich Malik as a project engineering manager and resides in North Carolina. Okay, let's go ahead and get started. I'd like to ask Hunter to take it from here.
Thank you, Ms. Michaela. Welcome, everyone. Here is the agenda for today's presentation. If you attended the part one, we kind of covered pressure sort of in general, the different pressure scales, which can be rather confusing, and got into differential pressure applications, the simpler applications, simple level, orifice plates, that kind of thing. This particular webinar is going to be aimed at the more complicated applications, particularly steam drums, which bedevil technicians all around the world, and also diaphragm seals. Diaphragm seals can be a source of a lot of trouble for maintenance and instrumentation folks, and there's a lot of things that are happening there that most people don't realize, and so they see bad performance and they immediately assume it's the transmitter and or the system itself, and then they replace it with another one only to get exactly the same problem. So talking about the diaphragm seals, actually what's happening so that you better understand what you can expect and ways, of course, to eliminate or reduce those problems. As Michaela said, we'll have a Q&A session after the first section and then again after the second. And without any further ado, I will get started. Kind of as a quick review, let's talk about level transmitter, standard differential pressure level transmitter on the bottom of a storage tank. It's measuring the pressure there. The pressure it's going to see is going to vary with the level of the liquid. And so if you've got 23 feet of, let's say, water, so that's got a specific gravity of 1, then you can calculate what the zero and span of the transmitter need to be in order to give you a 0 to 100% reading. At 0, you determine the pressure at 0 level, and then span, of course, at 100% level. So 0, there's no water, there's no pressure, there's 0 inches. That one's pretty easy. The span is a little more involved. It is tied to the level of the water in the tank and the level of the liquid in the tank and the specific gravity of that liquid. So in this case, it's 23 feet times 12 times 1, or 276 inches. So we calibrate at 0 to 276 inches, we get a 0 to 100% reading. Life is good. Until we add a blanketing system onto the tank. Now you've got a pressure in the vapor space that's going to push down the level transmitter, and it's going to see that additional pressure all the time. So in this case, at 100%, you won't read 276, you read 276 plus 10 or 286, so it'll seem to be off scale. And of course, if that pressure in the vapor space varies, then the error will vary. Well, that's not very good, and to fix that, usually what you'll see is a tap tied to the low port of the transmitter, run up to the vapor space of the tank, and now you're basically subtracting off the pressure in the vapor space, so you're back to your 276 inches. Everything works well. One kind of problem with this particular application is that vapors tend to work their way into the tubing and they're condensed, and that will start to build up a level in that low side, which will actually drive your reading downscale. By adding some kind of a nitrogen purge or a purge meter, and maybe air, depending on the liquid in the tank, you can keep those vapors out of there and ideally keep it dry so that it works all the time. Let's talk a little bit about some other ways to get that same measurement. One way is a bubbler. Bubblers are very old technology. I've actually have been used for years and years. They've kind of fallen out of favor because of some VOC issues, and we'll talk about that. But the idea is pretty straight up. You run a tube or a pipe down into the tank, and it goes all the way to the bottom. You don't want it all the way on the bottom because then the liquid can't get out, so you usually cut it at a slight angle at the bottom. But what you do is you got a level transmitter, a differential pressure level transmitter on the top, same calibration as you did before, but now you basically blow bubbles out the bottom. And the amount of pressure it takes to blow the bubble out the bottom is dependent on the level in the tank. And because you've got the low side of the transmitter tied to the vapor space, you basically get exactly the same reading. And these work very well, provided you don't get a lot of sludge in the bottom of the tank, and you don't mind the emission. Of course, you're blowing bubbles through the liquid, and if it's a solvent, then you're going to tend to generate a lot of emissions that companies are trying to avoid. So bubblers in a chemical that is going to cause VOC concerns, they're going to not like a bubbler. They're going to look at some other technology. And another technology might, in fact, be differential pressure seals. And we're going to talk about this particular application a great deal later, so I will not beat up on it at this point. I just kind of wanted to introduce the ideas of differential level so we can talk about everyone's favorite topic, and that is steam drums. Steam drums bedevil a lot of folks, and in order to help with that, we're going to go over it and so that you guys can get caught up. Now let me ask you this. If I tell you that we've got 36 inches tap to tap in a steam drum, can you tell me what the calibration is? Of course, you guys can't answer directly, so if anyone said yes, unfortunately you're not right. You need to know a great deal more than just the tap to tap height. You need to understand the specific gravity of the water in the drum, which will depend on what the drum pressure is, which we'll discuss here in a second. You also need to know the specific gravity of the water in the legs. Usually most people heat trace the legs in order to keep them from freezing. The temperature of the water will determine the gravity, which affects the calibration. Of course, you need to know the tap to tap height. I gave you that at 36 inches, so that much you know. Last question is, do you need to know the height from the low tap to the level transmitter, that lower section? The answer to that is no, you don't. If you have the same heat tracing on both the legs, then they're going to be the same length, and because they're the same length, they offset each other. And so it really doesn't matter whether that's 10 inches or 10 feet, as long as they're the same temperature, then the net effect of the reading is nothing. And so you don't have to worry about that part. You do, however, need to know the other items. And let's talk about those items. We'll start with the gravity of the water in the drum. That specific gravity depends on the water temperature, and the water temperature depends on the pressure. Of course, the steam drum is boiling water, and the pressure determines the boiling point of the water. And you can see here that as you go from 0 pounds pressure up to 800 pounds, the boiling point rises from 212 to over 520 Fahrenheit. Of course, the gravity falls with temperature, and so it goes from 0.96 all the way down to 0.769. So the gravity depends on the drum pressure, and that's a key point because a lot of people expect the reading to work all the time. If the drum is not at its normal operating pressure, the reading will not be accurate. The next item is the water in the legs. As I said, most people heat trace those. Some people use electric trace. Some people use steam trace. Some people don't trace them at all. If it's inside and there's no issues for freeze protection, then they might just leave them right there, in which case they would just be ambient. The important point is that whatever you do, if you heat trace it, electric trace it, steam trace it, whatever, you need to leave that tracing on year-round because you need the temperature to be the same year-round. A lot of folks will realize the trace is on, the steam trace is on in the summer, they'll go, oh, well, I don't need that, and they'll probably turn it off. And then the readings in the level drum go bananas, and no one understands why. It's because that gravity of that liquid affects the reading. So let's do those calculations and figure out exactly what this particular steam drum would be calibrated to. I've given you that the conditions are 600 pounds of steam. The backcourt gravity is 787. We're using 45 pounds saturated steam to heat trace it. So that gravity is 0.923. Now we have everything we need. We're going to, in order to calibrate or figure out the 0% setting, 0 level setting or 4 milliamp point, we need to figure out what the high tap is seeing minus the low tap is seeing, and that will be our calibration. Same for the 100% level setting. We need to check the high, subtract off the low, and then get our reading. And so we'll start with the low. And we have 0 level. We have nothing in the drums. So the high side reading is pretty easy. It's 0 plus the lower leg water, which we said we don't care about because we're going to read the same thing on the low side as well. So we can ignore it. Our low side, we've got the lower leg water again, same thing. So it's just being subtracted off. But we have 36 inches of 0.923 gravity water. And so that will give us a 0 minus basically 33.23, or a calibration for 4 milliamps of negative 33.23. That seems very odd. That kind of blows up some tech's mind, but that is the actual calibration for the 4 milliamp point for this transmitter. 100% level. Now we've got liquid, we've got water in the drum. We've got 36 inches of water. Its gravity is 787. So that's the high side. The low side has the same 36 times 0.923. We subtract the 2, and we end up with negative 4.9 inches of water column. That is the 100% or 20 milliamp point for this transmitter, negative 4.9 inches. That can cause some calibration issues, these negative numbers, and thankfully Roy is going to show you how to address them. And with these calibration settings, I think at this point I'm going to turn it over to Ned, who will talk about some of the logistics, I guess, of calibrating these drum levels. And take it away, Ned, it's all you.
All right, Hunter, thank you very much. That was some great information, and you're going to see Roy do a calibration using the numbers that Hunter just presented, but just want to go over some issues before you start doing an actual calibration, and I always like to push the idea that you need to get educated. So I'm just taking advantage of an ISA publication. There's an excellent book. It's by a guy named Jerry Gilman, so this is available from the ISA bookstore. But, you know, in addition to something like this, there's courses you can take, or, you know, get with your vendor on the steam drum instrumentation, and you can learn a lot of things about your particular application. I stole this image from Jerry Gilman's book, and so it's similar to what Hunter just showed you, but notice on the right it's got like a correct installation, and then maybe over here on the left it's got a bad arrangement. So might give you some insight on how you have your system set up. Over here it talks about a blowdown valve. So, you know, prior to calibration, you can open this up, and you want to clear out any sediment that might have built up around the transmitter. But, you know, if you're shooting steam through the blowdown valve, don't do it for very long. You could end up exposing that high temperature to the transmitter, and you can end up cooking your transmitter. So if we go through some steps here, down here, we'll make some points on, you know, you're going to isolate the transmitter from the process, so you want to, you know, bypass it also out of your DCS. And this is another got you. Many times you make a mistake here and you think you're working on one transmitter, you've got it isolated, but the fact is you're on a different transmitter, and suddenly you're causing the plant to shut down. So make sure you're following good procedures here. And another gotcha is you really, Hunter had mentioned about the steam tracing, and you should leave that active. And mainly you want to have consistency. So the calculations that Hunter just went through, if you turn the steam tracing off, all those numbers go out the window. So if you leave the steam tracing in place, it allows you to have consistent testing, and it works 100% of the time. Okay. So here's those numbers that Hunter just went through. We want to calibrate these calculated numbers to be 0 and 100%. So it is kind of backwards because they're negative numbers, but you're going from a lower vacuum to a higher vacuum to get 4 to 20. So you'll pretty much, once you have these numbers, you can calibrate the transmitter sort of in a normal fashion where you would check it at 4 milliamps and then run the pressure up and check it at 20 milliamps. And you make adjustments as you normally do. Once you've made your adjustments, you can then return the transmitter back to service. When you turn things back on, you want to give it a chance to get back into its normal state. And just kind of a reminder, if you had turned off that steam tracing and now it comes back on, until things get normalized, your calibration or your readings are going to be wrong. So make sure that things are looking normal and back in place. And then when you feel like you got everything right, if you've got some other way to check the level through some kind of sight glass or mechanical level gauge, you could adjust the 0 to make everything match up. So if your calculations were a little bit off, this is a place where you can adjust the 0 to, if you think it's off a little bit, and bring it back in line. So those are some of the points I wanted to make, but now we're going to let Roy actually demonstrate a calibration on this particular transmitter. So Roy, I'm turning it over to you. Have at it.
Thank you, Ned. So one thing that might not be obvious to you is what to do in extreme temperatures when you're calibrating. 3 hours ago, this news flash came up. Arctic temperatures invade U.S. So I would recommend that you probably use a calibration hat, something similar to this, just to keep yourself warm and avoid frostbite. But aside from that, let's look at the actual calibration itself. Allow me to share my desktop. As a technician, your job is to do whatever calibrations come up for the day. So I have a work order that includes 2 different calibrations, and they're listed right here. They're 2-level calibrations, LT250 and LT251. So first of all, let me load these onto my calibrator. I'll just hit send, and that's pretty quick. It's already loaded. Now, one other thing before we look at the calibrator is let me look at the position itself, or the tag that I'll be testing. Now, the second calibration that I'll be doing is a little more complicated, so I wanted just to print out some trimming notes or calibration notes here from the software. So let me just open up that document, and I will bring this up later. This is more about what we're going to do next. But we've got that. Let me fire up my calibrator here. So what we're looking at is a representation of my actual calibrator. And with the video, one thing to note is that you can double-click on your video to enlarge it, but if you wanted to make it smaller again, on the top right-hand corner is an exit full screen button, so you can just press that and get back to normal. But this is the calibrator that I'm using. and this is the device that I'm testing right now. So this is a Rosemont 3051. I've got an isolation manifold here on the bottom. So I'll be connecting on to the high side using a 30-degree pipe fitting, and the low side is open to atmosphere. I'll be connecting to the terminals on the back, the plus and the minus, for the power as well as the communication. Let me get my calibrator plugged back in here. So I wanted you to know that we're not just looking at an emulator, but you're actually looking at the screen on my calibrator. The first test that we'll do is LT250. So I'll press that, and this shows me where I plug in. So my output of the transmitter, I just follow these directions on the bottom, go right here, and I'm using this pressure port on the left-hand side. Let me make these connections. As I'm hooking this up, I want to remind everybody that we've done a number of videos in this past year, and the most recent ones have come from input from you. At the end of this video set, we'll ask you some questions. There will be a survey. Please take the time to fill that out and let us know what type of videos you'd like to see in the future. In the direction that we've received previously were calibrations on switches. So we did a video on doing switches, on calibrating smart instrumentation, calibrating pressure, and then finally calibrating level. So right now we're on part 2 of pressure. Using the numbers that have been shown to us already, we see that to calibrate this transmitter, our 4 milliamp number is minus 33.23 inches of water, and our 20 milliamp number is minus 4.9. So we need to supply a vacuum. To do that, I'm actually using a pressure pump that has a fine-tune knob on it, and by simply running the fine-tune knob backwards in reverse, I'll be generating a vacuum, and that'll be enough to do this test. So I'll start off here by hitting start. The top left-hand window is a representation of our actual pressure itself. The bottom right tells us where we're going, so I need minus 33.23 inches of water to get our 4 milliamp point. And you see a gray bar that I'm heading towards, and that means that I just need to get into that gray bar window. I don't have to get it exact because we'll calculate the error based on whatever our input is. In the top right window, we're seeing a live measurement of our milliamp output from the transmitter. And above the graph on the right side, you can see the actual error itself. The black line in the middle represents perfect, meaning there's no error between the input and the output. And the blue dotted lines represent our tolerance. So we're allowing a 0.5% of span error. So visually, if we were outside of 0.5% of span, then it would be outside of the blue dotted line. So as long as all of our test points are within the blue lines, then we know that it's a passing situation. And I do have a 5-second delay in between each test point. This is a fully automatic calibration. The only thing I'm doing is changing the pressure on the input. So we just did a 3 up-down test. This is the final test point. Now, as a technician, I need to know, did it pass or did it fail? So based on the criteria that we gave a 0.5% of span error tolerance, and we can see here that our largest error was 0.155% of span. We can also tell that we calibrated LT250, and calibration doesn't mean that there was an adjustment made. A calibration is a test against a known standard. So we are calibrating this transmitter against a device that has traceability and has been calibrated itself, and that's the calibrator, both the pressure module and the milliamp measurement. We can arrow down, we can put in notes if we want to, but here's a graph that shows the calibration that we just performed, and we can tell that it passed. And we can look at the raw data itself. And maybe you had maybe you do a visual inspection on every calibration that you do. So in here I've got just one question: visual inspection passed. Was it clean and everything was connected properly? And I'll just put a check mark in there to say yes. So let me save this. We'll save this as found. Now, because it passed, we don't need to do anything else. If we wanted to, we could do a trim, but this passed, and that's all we're going to do here. At this point, let me turn this over to Michaela if anyone has any questions.
Thanks, Roy, as well as Ned and Hunter. Okay, so like you said, we're going to go ahead and jump into the Q&A portion. This is the first Q&A portion. We will also have a final Q&A session that'll be a little bit longer towards the end of the webinar. So I ask each one of you to go ahead and submit a question into the Q&A box. Now, I know there's two boxes there. There's a chat box and there's a Q&A box. Submit it into the Q&A box. And because we're not opening up the phone lines for participants, please submit your questions into the Q&A box and not the phone lines. We've already received a question here. First question comes from Stan, and it was, what was the 31% significance?
So I'll take that one. So Stan, the 31% significance means that we used up 31% of our tolerance budget or error budget. So we had 0.5% of span allowed, and we used up 31% of that.
Yeah, let me add to that. I like to call, where we call it significance, I like to use the term error budget. We were basically 1/3 of the way out of our error budget of 0.5%. It's another way to maybe state it.
Okay.
All right, thanks. Another question that came in from Charles. Do you always suggest an up-down cal versus just an up calibration?
I'll take that one. This is Ned. You know, it depends on your practices and things, but for a differential pressure transmitter, I would recommend doing an up-down test. You mainly are wanting to check for hysteresis or verify that the diaphragm, whether you're pushing the pressure in or going up pressure versus when the pressure's dropping, does it retain some memory and cause a difference in the measurement, whether you're going up or down. Typically, if you're doing a 5-step pressure test where you go 0, 25%, up to 100%, to me it would be better to do a 3-step up down. So you go 0, 50, 100%, and then come back to 50, 0. You're doing the same amount of work, but you're checking for hysteresis. On the other hand, if you're checking a temperature transmitter, nowadays they're pretty good and very linear. It's kind of a waste of time to do an up-down test on the instrument like that. So I guess the best answer is to use your experience, and if you're seeing a straight line every time you go up and down, then there's no point maybe in coming back down. But for pressure in general, I would do an up-down calibration.
All right, thanks, Ned. Next question is, I just do not understand fully the physical meaning of steam trace. Would you please elaborate? Thanks.
All right, guys, I'll get that one. If the wet pass on the boiler drum, I mean, if you're using the regular differential pressure transmitter, you're going to connect. You can have 2 connections on the drum, one at the low level point and one at generally the high level point, and you're going to run tubing down your transmitter. That water is just sitting there, and so it is not going to be very warm. It'll be warm within a foot or so of the drum, but once you get more than about a foot away, usually the temperature will fall off, and so it will drop to ambient temperature. If you're in warm, sunny Florida and it never freezes, then you're fine. But if, like, actually, I believe Florida's supposed to get 20-degree weather today, or this this evening, and so in that case, you will trash your transmitter. You'll basically freeze your lines and destroy them. So you heat trace them or steam trace them to protect them. Heat trace can be electric. Steam trace is usually you either run a piece of steam tubing next to the tubing that you're running to your transmitter, or you can actually buy that as one continuous piece. Either way, you have saturated steam going through it to keep it above the freeze point and keep it from freezing. Good.
All right, next question says, I don't really get the theory about the steam drum pressure calculation.
I guess I'll take that one too. I mean, it's any differential pressure transmitter, whether it's on steam drum or level or whatever it is you're doing. In order to calculate the calibration, you have to understand the 4 milliamp point, the pressure the transmitter is going to see at 4 milliamps, and then the pressure the transmitter is going to see at 20. And so it's probably easier to go back through the steps and see what I was doing. I kind of had to move through a little quickly. But basically what you're doing is it's going to be high pressure minus low pressure. And if you go back through the slides, and they'll get posted after this, you can see basically I was calculating the high pressure minus the low to get the 4 milliamp point, and then doing the same thing for the 20 milliamp point, and that gave you the calibration for the transmitter. If you're a tech, usually you're given that information. But if it's a new installation, then you have to do it yourself.
Okay, next question. Coming to the calibration device, what is happening inside and is getting calibrated?
I'll try to answer that one. I'm not quite sure what you mean on that, but if you're talking about the calibrator that Roy used, Roy showed that pump, and he's running a hose from the pump to the transmitter and the calibrator. So when he changes the pressure with that knob, the calibrator feels it, and so does the transmitter. So your calibrator is traceable to some standard, and you're comparing that traceable measurement to what the field device, in this case the level transmitter, is measuring. And if they're off, you need to adjust them. And somebody's asked a question here about making an adjustment. We are going to demonstrate an adjustment on the next calibration that Roy does. So we'll actually go through that and you'll see it.
To clarify on Ned's comment, I think the question, he's confused. The calibrator is actually acting like a handheld. The calibrator is communicating to the transmitter, and so although Roy didn't make a change, he will make a change in the next one, and you'll see basically what he's going to do is he's going to do a zero trim and an upper trim and a lower trim, and it's the same as you do if you had a handheld tied to it. It's just the calibrator is taking that role.
Okay, great. Thanks, guys. I think we have time for maybe one or two more. Next question says, we've used antifreeze in the low steam drum leg to help stabilize. Any thoughts on that? Pros, cons? And I think you made another note that says, I realize that the SG calcs would be different.
Yeah. In order to answer that question, as long as it's consistent, life is good. So if you can put antifreeze in there and leave it in there, and as long as the gravity of that antifreeze doesn't change appreciably, then everything will be fine. I mean, and as long as the tech understands that it needs to be there. I've seen a lot of people use antifreeze, and that works great for a while, and then somebody goes out there and blows the line down because they don't realize there's antifreeze in it, and suddenly now you've replaced it with water, which is at a very different gravity, and now your reading is off. So while antifreeze works fine in the short term, everyone needs to understand it's there, because the moment you do a blowdown, you've ruined it unless you refill it again. So most people try not to go there. It's better to go with a heat trace of some kind, whether it's electric or steam, so that it's at least consistent. But it works. You just need to compensate for that when you do the initial calculations of your calibration.
All right, we'll wrap up this last Q&A with this final question, and then we'll move along. Are there any alternate ways for measuring DP, like capacitance method, resistance method, being implemented in industries?
I can answer that one. Absolutely, yes. Especially in a steam drum, you can use radar. You can use capacitance has got issues, especially. I would be a little leery of capacitance because the conductivity of the water is extremely low, and a capacitance transmitter is very affected by that conductivity. And so if there's very little there to begin with, then just a slight amount of change can make the reading change. Radar is going to be more consistent. Of course, there's eye highs, which are basically spark plugs going up and down, but they work reliably regardless of the drum pressure. And radar generally can work pretty well too. You just got to be sure that you buy one that's made to handle the temperatures. Only recently have the radar transmitters reached the point where they can take the higher drum pressures and not burn up.
All right, thank you guys. We're going to go ahead and move along to our second portion of the webinar. And during this next portion, feel free to submit your questions at any time into that Q&A box, and we can just collect them at the very end and answer them for you. All right, Hunter, you can go ahead and take it from here.
Thank you. All right, now we're going to DP seals. And as I mentioned in the initial part of the presentation, these can be a source of a great deal of problems for technicians. And we're going to give you a lot of the specifics and the details behind the scenes so that you understand what's going on, and then you can take that into consideration when you're choosing a transmitter and also installing it, and of course calibrating as well. There are three general big types for transmitters. You have a pad type transmitter, that's the one in the top left corner. It's got a single seal. It's usually connected, bolted or welded actually onto the transmitter itself, and it's bolted onto the tank. Then the low side of that transmitter is vented, so for an atmospheric tank it works fine. The next type is a pad type with a single capillary seal. In this case, you've got the same pad type seal on the high side, and the low side has a remote seal and connected to the transmitter via a capillary, which can be a few feet long, can be multi-feet, 25, 30 feet long even. And the last one is what we call a dual capillary seal. You've got two usually identical seals. Usually the capillaries are identical lengths, although they don't have to be. And they're tied to the low and the high side of the transmitter. And they all have their good points and they all have their bads. So let's go through kind of the components first, just so everyone understands the pieces. Of course, you've got the differential pressure transmitter. It's a standard transmitter. There's nothing special about one that's used in the seal systems. They usually just take any one and then hook up the seals to it. You've got the capillaries. The capillaries are flexible, usually stainless steel. They're fairly small, but they can be different size diameters. Some of them are covered in like a Teflon coating to protect them from corrosion. And they're fairly flexible. If you keep them, you can damage them, but they'll take a fairly decent amount of beating without being damaged. The seals themselves are measuring the pressure itself on the process. These are flange types. You can get screwed fittings, you can get ring joint fittings, you can get virtually every fitting you can think of. And they hook up to the tanks or to the piping or whatever in order to measure the pressure. And
hey Hunter, sorry, real fast. Can you make sure your mic isn't brushing up against your shirt?
Oh, I'm sorry.
It's making a little bit fuzzy noises here.
Okay. Got it. My bad. The fill fluid is filling the whole system. When the vendor puts together this package, you have to special order it. You have to order all the different parts, and then he'll put it together and send it to you. And he evacuates all of the vapor out of this system. If there's any vapor inside of it whatsoever, it will not function very well, or it may not even function at all. So he evacuates all the vapor out and completely fills it with the fill fluid. What's important here to know is that once it's put together, it's put together. And so if you get the wrong fill fluid, or you pick the wrong capillary, or the seal doesn't fit, then you're toast, and you have to send the whole thing back to get it fixed. These are generally not repairable just because it's so difficult to do. And so getting it right the first time is really your only option here. So let's talk about the individual pieces, and we'll start with the seal. As I mentioned, the seal basically measures the pressure of the system and sends that onto the transmitter. And it kind of works like the brake system in your car, right? So when you put pressure on the seal, there's a very, very thin diaphragm that's pushed in, and there's liquid behind it, and that liquid pressure basically gets transmitted to the transmitter, so that's how it reads it. That diaphragm is very, very thin. It does not take much to damage it at all. There's been a lot of cases where the mechanics forgot to hook up, put the gaskets on there, and they just bolted it up and they ruined them. You know, it doesn't take much at all to ruin the diaphragm, so you want to be pretty careful with it when you hook it up. The fill fluid can be a source of problems for a whole lot of people, and we'll talk about all that. But the fill fluid itself is usually a silicon-based oil, but it can be glycerin, it can be a halocarbon, it may be propylene glycol. There's some special fill fluids, and they all have their good and bad points. The major issues that you can run into, first of all, is process compatibility. If a seal leaks, if it gets damaged, some fluid is going to go into the process. If your process is very sensitive to, say, silicon, and that's going to cause you a bunch of quality problems, then using a silicon-based fill fluid is possibly not what you want to do. Maybe you want to pick glycerin or something that may not cause you quite as many problems. It won't leak a lot, but if a little bit goes a long way, then that could be a major issue for you. Low process temperatures or low ambient temperatures can cause you problems on the fill fluid. The fill fluids themselves tend to be fairly viscous to start, and of course, the colder they get, the more viscous they become. And as they get progressively thicker, the response to the system gets slower and slower because it's transmitting that pressure into the transmitter, and so if it's very thick, it's going to transmit the pressure very slowly. So either low process temperatures or low ambient temperatures can be a source of problems for you. Another issue, and this was probably the biggest one, is vacuum and or pressure and or temperature, or worst case, both. If you've got a high vacuum situation, it will tend to boil the liquid inside the system. Once you boil the liquid, the fill fluid, you've virtually ruined the system. It probably will not recover. And so temperature obviously is going to tend to boil the system. The combination's even worse. Now I've got a vacuum that's lowering the boiling point, and I've got a temperature that's driving it there. And so you can pick fill fluids that are specifically designed for high vacuum or temperature conditions, but the problem with that is that they're high viscosity fluids. And of course, if they're high viscosity to start, and now I've got low ambient temperatures in the mix, they're going to ruin my response. So picking the fluid is very tricky, especially in a vacuum application, and you want to consult a vendor or be certain that you know what you're dealing with before you pick one. Let's talk about temperature expansion on the seal. This is another source of problem. If you've got process heat, if the temperature of the process is going up and down, changing, it's going to tend to make the liquid inside the seal expand. And of course, as it expands, it's going to increase the readings that the transmitter sees. Now, the real pressure may not have changed, but the transmitter will see a change. The zero will start to move around on you because of the temperature expansion inside the seal itself. So that can be a source of problems, and I've seen situations where they zero a transmitter, then they put liquid in there, and suddenly, you know, they empty it, and now it's off again. Well, the reason why is because they put a warm liquid in there, and now it's hot. So you need to understand that varying temperature will generate zero shifts in the transmitter, and if you're looking for super, super accuracy and repeatability, this may not be the situation for you. Now, there's ways around that with tuning and those kind of things, and Ned will actually discuss that a little bit. But all of these things can impact the accuracy of the transmitter. one other thing that's worth noting is that the larger the seal is, the more sensitive it is, and it's able to read lower process pressures, down into the inches of water. But the larger the seal is, the more volume of liquid you have in it, and so the more it's prone to zero shift due to process temperature variation. So, you want a big seal to get nice, good, sensitive readings, but if you get a big seal, you have more temperature problems. All right, capillaries themselves. That seems straightforward. How hard can it be? All it's doing is just a tube transmitting the pressure from one side to the other. And that's true, but there's some issues there as well. Unfortunately, large diameter tubes respond faster, especially if you've got a viscous fill fluid. If you've got a fairly big tube, then it's going to transmit the pressure reading quicker for you. However, you've got a higher volume with a bigger tube. And so if you've got ambient temperatures changing, so the outside temperature is getting hot or cold, then that will make the fluid inside contract or expand, and that will shift the zero around. So you want a big tube to get good response, but the bigger the tube is, the more ambient shifts that you'll see. Now, if the capillaries are the same length, they'll usually offset each other. They're usually seeing the same ambient temperatures. If they're the same length, they'll respond about the same way, and the net result to you is a much reduced impact. So a dual capillary arrangement will usually be better about this kind of a problem. The last one I'll mention is one that I learned the hard way, and so I thought I would pass it on to you so you can avoid the same mistake. Let's say you're trying to measure a very low differential pressure, say 10 inches of water in this particular case, across, you're measuring the pressure drop across the column. And it's a very tall column, so I need two very long capillary seals, in this case, two 25-foot seals. You would typically buy a low-range transmitter because you're trying to measure a low reading. And that's, in fact, what I did. But what I failed to recognize was that I had 25 feet of capillary above the transmitter, and the weight of that seal fluid, which has got a gravity of approaching 0.9 to 1, depending on what you're using. So that weight on the low side is basically driving the zero down. And I've also got another 25 feet of that same liquid pulling on the high side down. The net result is I have a zero shift of 560 inches. If you were going to calibrate this transmitter, you would calibrate it negative 560 to negative 550. But if you bought a low-range transmitter, as I unfortunately did, you can usually only shift the zero 5 to 6 times the maximum span. So if you buy a low-range transmitter with, say, a 25-inch cell on it, you can shift it 5 or 6 times that, so maybe 150 inches, and I was needing to shift it 560. So I had to send the whole thing back to get a mid-range cell that would let me shift the zero the way I needed to. Painful lesson. Try to avoid it if you can. All right, transmitters themselves, and these are the individual types, because we'll talk about the pros and cons of each. If I take a single pad type transmitter here and put it on the bottom of my tank, usually it works pretty well, but it is subject to some zero shift due to process temperature changes. If the tank temperature is changing, the cell liquid is going to expand and contract, and it will shift your zero around some. And you can buy tuned units that actually sense that temperature and adjust for it, and that can make that reading better. Another problem is this generally only works on vented tanks. If I want to hook it up to a non-vented tank or a pressurized tank, I can hook up the low leg, but I've got to put some kind of a purge on it to keep the condensation out. So now we'll go to the single pad, single seal type, and this is the one we showed earlier in the game. The major issues here are the single capillary tube tends to shift to zero due to ambient temperature changes. I've got the ambient conditions working on the long capillary, but probably not so much on the pad type on the bottom, and so I will tend to see a mismatch and see some changes with outside temperature. It may be subject to zero shift due to process temperature unless both seals see the same temperature. Now, usually, if you've got a warm liquid in the tank, the bottom will be warm, but the top may not be. And so the temperatures may be different, and so the effects may be greater. But if they're roughly near the same temperature, then the changes aren't very bad. Finally, we'll talk about the dual seal. Of the transmitters, this probably is the better one. The ambient temperatures are offset because the capillaries are the same length. They're balanced, basically, so they tend to ignore the outside temperatures more. The zero shift due to process temperature, kind of the same here. You've got both seals. As long as they see the same process temperature, you'll be fine. If one sees a different temperature than the other, then you may get some offset. That really depends on application to application. I think at this point, I will turn it over to Ned, who's going to talk about purge rings, which can be incredibly useful from a calibration perspective. Take it away, Ned.
All right, Hunter, that was great. A lot of good information there. Let's see if we can talk a little bit about the logistics of installation and being test ready. So, Hunter went over a lot of good details on that, application and what's the best thing to use. Also, I highly recommend you try to consider how you're going to test these transmitters. As Hunter said, they're fragile. You've got these capillary tubes flopping around, so it's really good if you can design up front how you're going to test these types of transmitters. And one thing I learned just in preparing for this is you should utilize flush rings. And as you can see in this picture, I just grabbed this off the internet from a supplier. Here's the rings over here, and you can actually sandwich it between the capillary and the tank. So this gives you a way to get access to the pressure seal, where you can stimulate it with the vacuum and pressures that you need to do without removing it from the process. And these things are so sensitive, you really need to come up with a way to test these in situ, in the process, not try to pull these off and calibrate them in a shop environment or something like that. Again, I'm going to emphasize, get educated. The vendor product manuals are very thorough in this area, so you should have a lot of good information at your fingertips. Focusing a little bit more on installation, you want to make sure that everything's placed properly and match up to your calculations. Let me emphasize, those seals are fragile. You should always be using gaskets and make sure they're in place before you start bolting down and damaging an expensive seal. It's a big headache to have to send these things back, or you just end up throwing the old one away. You need to protect the capillaries, so in this case you should have some kind of tubing or guide to keep that capillary protected. So tubing trays would be a good option, and you should coil up the unused capillary near the transmitter, kind of bundle it up nice and tie it up to where it won't get disturbed or bumped maybe during cleaning and things like that. And you always need to be aware of ambient temperature. As Hunter said over and over, those can affect the measurement you're trying to make. Let's talk a little bit more about what Roy did earlier. He did a calibration, and let's talk about the procedure itself. When you're calibrating, you saw him check out those instruments from the database. Maybe you don't have a system like that, but maybe you have a work order. You're somehow scheduling that calibration to take place. So we observed Roy do an as found. At the end, everything was okay, so he wrapped up and moved on to the next instrument. So that's probably going to happen 80% or more of the time. On his next calibration, he is going to show where an adjustment is required. Doesn't necessarily have to fail, but we're going to actually demonstrate an adjustment and then perform an actual as left test, which is identical to the as found. And again, 80% of this time or more, you're going to be able to adjust it, and maybe you have to deal with some kind of deviation report if it affected your quality. In the case that you can't adjust it to pass on the as left, then you're going to have to deal with some kind of repair work order or initiate some kind of change where you can swap out, put in a new transmitter, and the new transmitter should obviously check out on this first line. I guess my point here is that you should have established procedures, and you want to follow those, do the same thing every time, and typically on important measurements, you want to perform as found and as left documentation. And then let's go through the actual steps for this tank that we're about to show. You want to isolate both seals from the process. So if you're using those flush rings, that allows you to leave everything installed in place. You want to make sure that both seals are at their normal position elevation. So if you have to disconnect something, you've got to take real care that you're keeping everything at the same level. Obviously, vent the seals to atmosphere. If you're using those flush rings, that makes it much easier. And if you're doing it as found, you want to record what's the pressure around 4 milliamps versus the actual milliamps, and then get on the high side of the transmitter and record the pressure and the milliamp reading near 20 milliamps. So then once you've determined whether if it does need an adjustment, then again you're going to vent. You're going to apply the span pressure to the high seal, or have it vented, do it at 4 milliamps, and then pressure it up and trim it at 20 milliamps. And then once you've done all that, you can close it all up, button it up, and put everything back into service. So it's pretty straightforward on that part. Then before I turn it over to Roy, I do have one last slide here. Let's go over some details about what Roy's going to show today. Roy has a Rosemont 3051S in his office. He's got this transmitter sitting on a desk nearby his calibrator, and then he's got the capillary running up to a shelf. So he has the capillary seal sitting on a shelf about 25 inches above the table. So imagine Roy's got a tank instead of his desk, and this is what he's going to be dealing with. So the range on the tank is 0 to 25 inches. And by the way, Rosemont refers to this as a tuned system because it does require some calculations, and they use a feature called a scaled range. So by using that technique, when the tank is empty, you're going to get 4 milliamps, and when it's full, you're going to get 20 milliamps. Well, this is all great for the operations people and the engineers and all, but the actual PV pressure, that the true inches of water that are sensed here between the pad here and the capillary here, is this calculated minus 3.46 inches at span, and at 0 it's actually minus 28.46. So kind of similar to what you saw Roy do earlier. And just, we didn't go through all the calculations, but these numbers are affected by the specific gravity of the process, but also the capillary fill fluid affects the specific gravity, and even this distance is a factor. So notice how the capillary is actually a little bit higher than the true tank of the level. So all these things get compensated to come up with these numbers. So from a calibration and trimming, these are very important, but at the end of the day, it's measuring a tank level of 0 to 25 inches. So both these calibrations we're doing today, I think I heard Hunter use it once, but these are real mind benders. I mean, as a technician, you really got to understand what's going on, and it's just not so easy. It is complicated, and so hopefully we've provided some insight. All right, so with that, I think we're ready to turn it back over to Mr. Roy. So let's turn on Roy here, and you can take it away, Roy.
All right, thanks, Ned. So you are a technician. It's now time for you to do your second calibration. We go to the site, turn on your calibrator. Now, in this case, Let me go into Documenting Calibrator. We've already done our first one. We can see a green check mark next to it. That means that we've tested it and it passed. The next one we have is LT251, and this is our level transmitter with a capillary. Now, as a technician, I'm looking here where to plug in, so I've already got it hooked up. The output of the transmitter is hooked up right here where it says loop, so we have loop power connected, and we're also able to do the heart communicator from those same two ports. Pressure is connected up on the top left-hand pressure port. And I actually have a T-hose on my pressure hose, so the pressure is going from my pressure pump, and it's also connecting the calibrator, and then the third leg is connecting to the transmitter. Now, because this is complicated, we need to break it down into chunks. And regardless of how complicated something is, if we break it down into small enough pieces, we can conquer it. So we have a before calibration note for the technician. Lower trim is the PV closest to 0. Enter PV to trim. And then the PV values are actually listed here right on the calibrator, so they don't have to, I don't have to have it printed out or written out on a piece of paper. And I'll explain what this means a little bit later. Let me hit check to continue on through this. Now, as found time. So we need to capture data. Let me hit the start button. This transmitter is actually 0 to 25 inches of water on the input, and then 4 to 20 milliamps on the output. Now, in this graph, you're seeing two sets of blue lines. Now, the black line in the centers are 0, and that's perfect. The blue lines that are farthest out, the dark blue, that's our tolerance. So that's 0.5% of span in this case. It could be plus or minus 0.5 inches or 2 inches or whatever you want it to be. But the outside dotted lines are the span itself. Now there's an inner set of lines as well. That's still passing, but what I've done is I've told the technician that if it passes, but it's outside of these inner bands, I want you to do an adjustment. So there's two ways to do a calibration. One is either it passes or it fails. And if it passes, you don't make an adjustment regardless of how close it is to being out of tolerance. And in this example, we're saying if the test results are within 75% of 0, then don't touch it. But if it's outside of that, then make an adjustment. And this, again, is an automatic calibration. The only thing I'm doing is changing the pressure. So the calibrator tells us that it did pass, but do an adjustment because it's still right on the edge. Let me arrow down to this. I could put in some notes here. So this inner band, what I'm saying here is that if it passes this threshold, then maybe it's a concern to our process itself. So it passed, but we need to pull it in underneath those guard bands. So let me save this. We'll save this as found. Next, we'll do an adjustment. So we'll click the menu button here on the top left. I'll click Start Communicator. Now, while that's coming up, let me show you this. So this was that document that I popped up from the calibration software. This is a note for the technician, and this is what my transmitter looks like. This pad seal here connected to the transmitter is on the high side, and then the remote seal with the capillaries on the low side. I have the low side vented to atmosphere, and I've actually got my pressure hose hooked up to the high side. And I do have a flange on the outside of it with a 1/2-inch NPT hole, so then I have a connector onto that 1/2-inch NPT and have that converted to a 30-degree pipe fitting so I can connect to it easily. These are my numbers. Ned showed you these earlier. For 20 milliamps out, we need to enter in negative 3.46, and for our 4 milliamp, it's negative 28. Now, for the Emerson pressure transmitters that I've got here, we need to calibrate the lower, do the lower trim on whichever one is closest to 0. So let me pull out my tablet here. And you know what? I'll bet you my tablet is probably thinner than yours. For those of you who are too young to know, this is a piece of paper. If it's not electronic, some people don't know what it is. But what we have here is a number line. We have 0. Anything to the left of the 0 is in the negative direction, and to the right is positive. So when we're going in here to do a sensor trim, the note here from the manual says the lower sensor trim value should be the sensor trim point closest to 0. So let's do this. We have 2 different trim points. So here's our number line again. We have 2 values, a negative 3.46, and then we have a negative 28.46. So which one is closer to 0? It's actually this one, which happens to be our 20 milliamp number. So it might defy logic a little bit, but in this case, don't make me say RTFM, but that's what we need to do here. So for our lower trim, we're going to do this number first. I'll bring up the calibrator. Let me do show all. I was showing just the measurable variables. So in this case, let me go into the communicator aspect. Trimming is underneath service tools, but if I go to configure, and there's guided setup, manual setup, I'll go into manual. There's the scaled variable, and this is what Ned was referring to earlier. The scaled variable means that we set up minus 28.46 to equal 0 inches on the input, and then minus 3.46 to equal 25 inches on the input. So that's how the transmitter itself does the calculations. Let's go back up and do a trim. Service tools, routine maintenance. Now, the menu structure will change based on manufacturer. And sometimes even different models of a manufacturer will have a different menu structure. So we want pressure calibration. Okay, which one do we want? 0, lower, or upper? We want to do lower, and then pick the number that's closest to 0. Warning loop should be removed from automatic control. That's fine. Now this top window is what's showing on the communicator. And the bottom 2 windows are what the calibrator is adding in. It's adding the ability to look at the pressure coming in and measure the current going out. So apply low pressure. We actually needed to generate that minus 3.46. So we need to get it to 20 milliamps, which is 25 inches of water on the input. So right now I'm just increasing using my fine-tune knob to get us pressure. And we would let this stabilize for a while. So let me accept that. I'll press OK when it's stable. And here's where we need to enter in negative 3.46. And send that over. All right, remove pressure. So that should have cleared out our 20 milliamp number. Now, the transmitter itself is working behind the scenes, so we have pressure calibration executing method in red across the top. So we can't actually do anything until it's done. It won't let us talk until it's done doing its mathematics. Lower is done. Now let's do the upper. So the upper is the furthest away from 0. So again, the furthest away from 0 in this case is actually our 4 milliamps. So negative 28.46. So I just need to vent my pressure, apply high pressure. You can see that we have 4.05 milliamps out. Let me hit the check mark. It is stable. And this is where we enter in minus 28.46. Hit our check mark. You'll notice the output here, the milliamps now are being trimmed automatically by the transmitter. Now we're getting a good 4 milliamps out. Loop may be returned to automatic control. We'll wait till this thing is finished. Now, we're actually done doing the trimming. This is how you trim a level transmitter like this with seals. Let me hit the X. So what have we done? We've done an as found, we've done a trim, and now we're going to do an as left. Let me hit the start button. You can already see that we're already far closer to our 0 than we were. And again, I do have a 5-second automatic delay in between each test point. So we'll just increase the pressure to get to our midpoint. And we're doing an up-down test to see if there's any hysteresis. And hysteresis would show up as a differential when we're coming back down. Maybe the midpoint going up will be in a different spot when we come back down. And that's hysteresis. And what I've got here is my capillary is actually sitting in the sun, and it's been affected. And that's what we're seeing here. So there's no hysteresis. Our two middle dots have lined up on both the up and the down. So in this case, it passed, and we get the message, do not adjust. The error 0.208 was our maximum, and a significance, meaning that 0.208 was 41.6% of our full tolerance that we had listed. So maybe I wanted to put in notes again, or just review the graph, or review how far out this was. And we could go in and actually do that trim on the span and get that so we have a completely flat line. But in this case, this will work just fine. And my inspection, I'll just put a check mark there so that I'll accept that. Click the disk to save. As left is already highlighted. Now I'm done. The results are stored in the calibrator. I could actually power down the calibrator, take it back into the shop, and unload the test results. Let me do this. I'm back in the shop. We need to get the test results out, so let me connect to the calibrator and just pull them over. I'll select both of those and receive. Done. Now, let me get a calibration certificate. I'll do a preview just so I can show it up on the screen. But this is the last piece of performing an automatic calibration that's documented. So we have the calibration certificate showing what it was, when it occurred, what the standard was, how much error, and who did it. So let me zoom in quickly. We have our graph. This was the first test that we did. Remember that passed, so we didn't make an adjustment. And here's the raw data, and here's who it was calibrated by. We could have an approval here if we wanted to. Let me go to the next one. This is the one that we just completed. And look at the graph. We can see that the red as found passed, but it was outside of our initial threshold that we wanted to allow. So that's why we did an adjustment. And like I said, we could come in and get the span perfectly flat, but in this case, this is just fine. We have our data. So with that, let's go ahead and turn this over to our second Q&A. Now, I do want to remind everybody that at the end of this webinar, you will receive a survey. So please take time to fill that out. But the most important thing of that is to let us know what topics you would like us to cover in future webinars. Thank you.
All right, thank you, Roy, Ned, and Hunter. This has been a great webinar. To conclude this webinar, we want to open it up for a question and answer session. And please enter your questions into the Q&A box on the right-hand side of your screen, not the chat toolbox, but the Q&A box. And if we're running low on time and we can't get to your question, then you're more than welcome to send your question to any of the presenters, and their email addresses are listed there on the slide. So to begin, our Q&A session. We'll start with a question that came in a while ago. So if there is any vacuum, then what can be done to make it calibrate as it does actually? I know we got some international folks in here, so we got to kind of determine what's being said here.
Well, I think you know, you can use a vacuum pump. It depends on the vacuum that's involved, but most people will actually get a vacuum pump and pull it down to where whatever the calibration requires. Roy is getting away with using his just squeeze pump and just using the dial, which works fine as long as you're talking, you know, 100 or 200 inches of water. You get much below that, then it's going to take a vacuum pump to take you much below that. You have any other comments, Ned and or Roy?
Yeah, I was going to say BMEX makes a vacuum pump, and there's others out there. We can pull about 28 inches of mercury, so that's probably like 350 inches of water on the negative side. So
I've got that right here. I just didn't need to use it for this small vacuum amount.
If it's a deeper vacuum than that, like where you were talking about the boiling situation or sparging, you know, you could use a vacuum compressor, and there's some techniques. If you allow a slight bleed on your pressure line, you can modulate how hard a vacuum it pulls. So you can simulate the vacuum to the transmitter either with a hand pump and use maybe a different one that Roy used if it's a deeper vacuum, or even utilize a compressor.
Okay, next question comes from Jerry. Are the capillary seal type DPs being replaced by electronic DPs like the E&H FMD71/72, eliminating the issues with the capillaries?
I can take that one. Or you got an answer, Ned? You go first.
No, I was just going to say that there's a lot of stuff going on in this area, so you can, instead of running that capillary, you can run a cable from the transmitter up to really a second transmitter, and that's a very good way to do it. And then the smart transmitter that's down at the base can do the mathematics to make a proper calculation.
Yeah, that's a relatively new technology, and I mean, effectively, what you're doing is you've got two different sensors, and then one transmitter that's talking between the two of them, and then doing the math, and like you say, transmitting the result out. Historically, that hasn't worked so well, just because you tend to stack your errors, and so your ability to really do a very accurate measurement was never there. Now the electronics are better, the sensors are better. I know that there's sensors out there now that don't have fill fluids in them anymore. They're all electric or electronic, ceramic and the like. You give up a little bit of your low-end sensitivity, but it is the way out. So if you're trying to get a very consistent measurement, it may well be that an electronic type transmitter arrangement is an answer for you. I don't know how the pricing works. I mean, you're basically buying two sensors and another transmitter to boot, so I'm not sure how that would compare. I've not really priced them, but that's surely a way to go about skinning the cat. There's also other technologies. You know, maybe instead of using capillaries in general, you go with radar or some other technology, which again, all of them have their pros and cons. Some work incredibly well in certain applications and are terrible in others. And so there is no magic bullet for solving an instrumentation problem. It's a matter of looking at your particular application and finding the best one for you.
All right, next question comes from Robert. He asks, where did you get the values of -3.46 and -28.46?
Michaela, let me on my calibrator as well. You can go ahead, Hunter.
I believe they came to you in a dream, did they not? Right? What we didn't really get into it, and Roy is going to show you here in a second. My personal experience, you know, you can calculate what the span is going to be. You know the liquid level, you know the gravity. You know, in this case, we said it's going to be 25 inches. We're going to say 0 to 25 is what you're reading. Now you're just trying to adjust the 0. What I typically do in an application is you get the seals installed where they need to be. You vent both the seals, and at that point, you read what the transmitter is reading, because you're going to have the, you know, you're going to have the liquid pushing on both sides. The height of the seals matter. The fill fluid matters. And while you can try to calculate all that, it's way easier to just get a reading on it, say, okay, I'm reading minus 28.46 with both of them vented, so my calibration is going to be minus 28.46 plus 25 inches, which is minus 3.46. And that's how Roy did this.
And I'm showing right now, can you see the MC6 on the screen?
Yes, sir.
So I'm looking at the measurable variables on this transmitter, and right now vented, the process variable is actually showing minus 28.46, so that's literally how we get that number easily.
Yeah, and if Roy moves that seal around even a little bit, you'll see that reading change. And so while it's possible to do a bench calibration of a seal installation, where you can see it moving, you just moved it a little bit. It doesn't take much. It's way easier to do it installed in place in the field, and that's why the flush rings are so useful, because you can just block the seal with usually with an isolation valve. You open up the flush rings and vent them, and now you've got a place to easily apply pressure, but you don't have to physically move the seal, because, like I say, their elevation sets this number. Thank you, Roy.
All right, next question comes from Charles. He said, slide 43 shows the DP with capillary measuring tank level. What is the advantage of using the capillary versus a simple GP on the tank outlet?
Can you bump back to slide 43? All right, there it is, 43. One more? You're 40.
One more.
Oh,
there we
sorry.
The other way. Go the other way.
There you go. You could absolutely use a GP, just a regular general purpose single pressure transmitter there, as long as the tank was vented. If there's any pressure on the tank, however, that won't work. And so usually the reason you do this is because you've got pressure in the tank and you need to basically subtract that off the reading so you can get a true level.
All right, next question. How easy is it to get the slip ring so you don't have to take it out of the process?
You can get those from the supplier of your transmitter. I think, you know, we were using a Rosemont, and there were all kinds of drawings of different sizes, and so I would say get with your vendor to get one that fits your application.
Yeah, when you spec out the transmitter and the skill system, one of the options generally is flush rings. Is kind of the typical term. They may change slightly depending on the vendor, but the flush ring is usually a ring that it kind of sets the seal off from the regular flange a little bit, and usually has one or more. It may have two taps in it that you can either plug, or you can put valves on, or you can do whatever you want, but it gives you a place to easily inject pressure or vent down and drain the liquid that might be there. And so typically you'll have an isolation valve between the tank, and then you've got this flush ring, and then you've got the seal itself, and you leave everything bolted in. You just close the isolation valve and then use the flush ring to apply pressure. Recognize that you will get liquid in front of those, especially on the bottom tap. So some flush rings have got a port on the top and a port on the bottom. So you open up the port on the top to let air in, and you open up the port on the bottom to drain the liquid out, so you don't have a liquid level there when you're doing the calibration.
You know, there's a related question, Hunter. I'd like you to answer it. Somebody's asked, do tank spuds inhibit using the flush rings? Do you know what a tank spud is?
tank spuds. The tank spuds, and he's going to have to call in and tell, or write in a little more specifics on what a tank spud is. I'm not familiar with that term, or at least what I would have thought it was wouldn't apply to flush rings. So, Robert, if you can give us a little more detail, we will take a shot at that. In the meantime, Michaela, you want to pick a different question?
Yeah, we can take this question. After understanding what you meant by steam trace, shouldn't I do the same in the case of capillary seals transmitters?
Oh, well, of course, freeze protection usually isn't the problem, although, like we talked about, ambient temperature can be. If you pick the right fill fluid, it can handle the conditions. Most people just kind of click the box and pick the standard fill fluid, which in most applications work fine. But if you've got a special application, like a vacuum application or a high temperature application, or you're in Alaska or something where your temperatures are going to vary a great deal and get very, very low, then you need to look a lot harder at the fill fluid. And there's a whole pile of different ones that you can pick. And you know, the vendors, you can go to their websites, whatever, and download this whole manual basically on fill fluids and all the different options and how they handle different temperatures and pressures. And so you just need to get the right one. And if you're not comfortable making that decision, then probably having a long, protracted conversation with your vendor so that he understands your situation, then he can pick the right one. A lot of times people don't think about the ambient conditions, though, so they don't tell the vendor, and the vendor just picks the standard one thinking that it'll be fine.
Okay. It looks like Robert expanded a little bit further. He said there are specific diaphragm seals designed for tanks connection using a matting tank spud instead of the regular flanges.
Flanges. Okay. Robert, I guess to answer your question, that's probably one that you're going to take up with your vendors, and just send him a picture and show him what you've got, and then see if he's got a particular connection that'll match up with yours. The flush rings work very easily on a flange connection, but if you have a screw connection of that kind, then it may not. So you may end up creating your own flush ring or some other, maybe you put in a couple of T's and taps or some way to easily drain that section of line. I'm not familiar with this particular connection that you're discussing, but I imagine if you took it up with the vendor that they could probably get you squared away or give you an option for ways that you can handle that. I mean, you don't need flush rings. I say you could just put a T there and then just have an isolation valve for the T. But the reason people usually use seals is because they got plugging, sludge issues, that kind of thing. And so if you add a bunch of extraneous piping on the end, it's going to tend to plug up. A lot of times the reason they have a big, nice seal like that is that it doesn't easily plug. In fact, you buy seals with extended diaphragms that actually extend into the tank somewhat to try to eliminate the pluggage problem, but it makes calibrating them a lot more difficult.
All right, we've probably got time for one more question here, and this one comes from Jerry. Is it possible to do an in-situ calibration when extended seals are used, no flush rings?
I would expect some vendors could offer some kind of an electronic calibration, but it would depend, the accuracy of that calibration would depend a great deal on how the sensor itself was put together. It might get you close, but I don't know that it would be a true calibration because you're not actually putting pressure on the seal. So you're doing electronic calibration, which means the insides work fine, but you do really, until you pressure it up and actually put pressure on it, you don't know. Extended seals are a bear to work on usually, and often the only way you can do it is to physically pull them out. But then, of course, when you pull them out, unless you get them right at the right elevation, your reading's going to be off. I can't answer that. I don't know if Ned, you or Roy have anything to add more than that.
No, I mean, my thought is you're going to have to remove it and then use what Roy's using in his office today, where he's got a mating flange with an NPT port, so it seals, it covers up the seal and allows you to make a connection with the hose to do the calibration. So unless, you know, that's kind of the point of my slide on, you need to design it up front where you can somehow get in there and make the in situ connection. That needs to be done from the very beginning, or considered at the very beginning.
All right, these have been some great questions. Thank you, all attendees, for participating. I want to thank our panelists for contributing to this webinar. If you'd like to discuss this topic face-to-face, you can visit our folks at BMEX at ISA's Power Industries Division Symposium, also known as POWID, June 7th through the 11th in Kansas City, Missouri. Or you can visit them at ISA's upcoming International Instrumentation Symposium, also known as IIS, May 11th through the 14th in Huntsville, Alabama. If you haven't registered yet for either of these, registration is still open. Simply go to isa.org to learn more. And if you missed any portion of this webinar, or you would like to watch the recorded version or share the recorded version with any of your colleagues or coworkers, we'll be emailing all registrants a link to the recording along with additional links for supporting information. So be on the lookout for an email from me within the next couple days, probably sometime next week, with that information. And like I've said, as well as Roy, just want to remind you that once this webinar closes, a survey will pop up in your browser. You want to take just a few minutes to fill out this survey and tell us about your experience at today's webinar. In particular, there will be a question about what topic you'd like to see us present for the next webinar. Please provide your feedback. We want our audience to help us determine what the next webinar should be on, and we definitely take a look at what each person says because we always want to improve our webinars. This concludes How to Calibrate Pressure Instruments Part 2. Thank you for attending, and we hope you acquired useful information and hope to see you again in one of our future webinars.